Hi guys, in this video what we're going to do is look at loans and mortgages, and specifically what we're going to do is look at something called an amortized loan. And these are the sort of loans that you get in real life, such as mortgages, car loans, etc. And the way these work are each of these loans are paid off by a series of regular payments. So you pay exactly the same amount every single year or month. Normally it's a month if you're looking at mortgage or if you're looking at a car loan, for example. Okay, so that's what an amortized loan is. If you want, you can read all this here and it'll go through the whole idea of an equation of value. But what we're going to do is we're going to find a formula that will tell us the amount of equal repayments for an amortized loan. Okay, so we're going to do that on the next slide. It's example 1 in the book, and what we're going to do is we are going to use what we've done in the previous chapters, i.e. geometric progressions, in order to work out what's called the Amortization Formula, which will tell us the monthly repayments for an amortized loan. Okay, so let's have a go at this. So it says here, Sandra takes a loan now of P. She agrees to repay this loan with a series of T equal yearly payments. A starting 1 year from now. The rate of interest throughout is I. Now, this is the important bit. It starts 1 year from now. Okay. So let's have a look at what's going to happen. We're going to draw one of these time graphs that we've been drawing so far. So there it is. Okay, and we are, at the moment, we are here. This is our present location. And we are borrowing P. Okay, so we're essentially taking a big chunk of money here to pay for a house, for example, or a car. So I might be borrowing 50,000 for a nice car, or I might be borrowing 300,000 for a house. And then what's going to happen is I'm then going to start making monthly payments. So after a year, because it says we're doing it in yearly repayments in the question. So after a year, I'm going to pay an amount. Then after 2 years, I'm going to pay another amount. And after 3 years, I'm going to pay another amount. And I'm going to keep paying that year on, year on, year on, until at the end, I pay my final amount and I'm finished. I've finished my loan. So what we're doing is we're trying to calculate, we're trying to work out the present value of all of these payments from this, and this, and we're trying to bring it all back to when I took my loan out here. So you can see here we're going back in time, which means that we are discounting, which means what's happening is if we discount, remember if we're going back in time, which remember from the other slide, it's whatever the amount is over 1 plus I to the power of how many years has come back or how many compounds has come back. So this first one, remember this is first year, second year, third year, and this is my year to the power of T here. And that means that what we now have is the following. We have this amount, whatever it happens to be. So it could be a monthly amount of, say, 500 quid, and it's over 1 plus I to the power of 1, because we've gone back. We're trying to get back 1 year, yeah? The second one then is A over 1 plus I to the square, because what we've done now, instead of going back 1 year, what we've done is we've gone back 2 years. The third one, just like before, now is going to be 1 plus I to the power of 3. And hopefully, guys, you can see that this one's going to be 1 plus I to however many years it was. So if it was a 10-year loan, then T here will be equal to 10. Now notice this is really important for an amortized loan, that there's always one time frame before you start making a payment. So when I buy the car or the house, what happens is I'm normally given a month's grace in order to do this. Or in this case, what it is, it's a year's grace, because we've been told it's yearly payments. But in real life, it's normally monthly payments that we start paying a mortgage off, or we start paying off a car loan, etc. Okay, so what we have then is we now know that this P, this, I suppose, the present value of all of these payments is equal to this plus this plus this plus this plus this plus this all the way up to T, which means now what we have is we have a sequence. So my P here is equal to, and you can see it's A over 1 plus I plus A over 1 plus I squared plus A over 1 plus I to the cube plus, and we're all happy there, guys, what we end up now with is A over 1 plus I to the power of T. Now this is just a geometric sequence where my A, my first term, is equal to A over 1 plus I. That's my first term. And how do I get from term to term, well, 1 plus I, I need to get to 1 plus I squared, the A's stay the same, so my R is equal to 1 over 1 plus I. That's what I'm doing. So all we do now is we stick it through the summation formula. Now if you can't remember that, I'll just come right up the top here. The S of n is equal to A1 minus R to the n all over 1 minus R. Remember that there is in your tables book. You're going to be using that a lot in this section, boys. So just make sure you have your tables book open. And all we're going to do then is simplify it and see what we're going to get for an expression, okay? So first thing we do then is P is equal to, because remember we've still got P is equal to there, and now just stick in everything that we know. So our A is equal to A over 1 plus I, and we've got 1 minus R, which is 1 over 1 plus I to the power of n all over 1 minus R, which is 1 minus 1 plus I. Okay, so now we're going to have to start simplifying this. The first thing I'm going to do is I'm going to look at this bottom bit, and I need to get them over the same denominator. So that's the first thing I am going to do. And if I do that, I'm just going to come up to here. I'll probably go underneath in a second. So I've got P is equal to A over 1 plus I. Okay, and that's multiplied by 1 minus 1 over I plus 1 plus I to the power of n. Okay, or T, whatever you want to call it. It should be T, doesn't matter, we'll use n. And then that's all over, and I need to get this here as a common denominator. So what I'm going to do is I'm going to multiply this by 1 plus I over 1 plus I. So let's just do that. I'll do it nice and slowly so you can see it. So we've got 1, and I'm doing 1 plus I over 1 plus I minus, now I've got 1 over 1 plus I, which means that I have the common denominator. So now P is equal to A 1 minus 1 over 1 plus I to the power of n, okay, and that's divided by 1 plus I as well, all over, and what we now have is 1 plus I minus 1 over 1 plus I. Okay, just to explain this step here, so this is A multiplied by this bracket, and this is A divided by the 1 plus I, so I can stick the 1 plus I under all of this if I want to, which is what I've done here, and you can see I've got a 1 plus I under this as well here. So that means that these 1 plus i's are going to cancel. So I'm just going to move the page down slightly, and I'm going to come back to the left hand side. So I've got now P is equal to, and I've got A by 1 minus 1 over 1 plus I to the power of n, and this time it's just divided by, we can do this in our heads, 1 plus I minus 1, so it's all over I. Now what I'm trying to do is I'm trying to get A to be the subject of this formula. So I'm going to get rid of the I on the bottom. So I've now got IP is equal to A 1 minus 1 over 1 plus I to the power of n, okay, on the right hand side. The next thing I'm going to do is I'm going to get this out here. So we're going to simplify this. Let's have a quick look, see what we've got. So if we do that, we get IP just stays on the left hand side. It's equal to A. What we now have in this bracket is we have 1 minus, and the top thing is 1 to the power of n. Now 1 to the power of anything is still just 1, so it's 1, and then if we get the bottom bit down, we've got 1 plus I to the power of n on the bottom there. So just make that bracket a bit bigger. So that's what we've got next. Okay, so I've got a fraction in here, so what I want to do, if at all possible, is I want to get this over a common fraction. I'm going to use exactly the same technique that we did over here. So whereas here we multiplied it by 1 plus I over 1 plus I, we're going to have to multiply this by 1 plus I to the power of n over 1 plus I to the power of n. So I'm going to do that next. So I'll just again show you what was going on there. IP is equal to A, and it's just a big bracket here. So what we have here now is, I'll just put the 1 so you can see it, and the blue bit here is what we're multiplying both top and bottom by, so 1 to the power of n over 1 plus I to the power of n, and then we've got minus 1 over 1 plus I to the power of n. So hopefully you can see what I've done there. Okay, and that means we can simplify the top now because it has a common denominator here. So what we now can say is that IP is equal to A And what we now have is 1 plus I to the power of n minus 1 all over 1 plus I to the power of n. So that's our new thing. Go up here again. So the next thing that what we're going to do is we're going to say, okay, we need to get that 1 plus I to the n to the other side. So this needs to go, because this is now a fraction, this needs to go across to there. So what we now have is IP 1 plus I to the power of n is equal to, and on the other side we have A, and we've got 1 plus I to the n minus 1. So that's what we're left with there. Now just trying to get A on its own. You can see that this is multiplied with this, so this needs to come underneath. And if we do that, we get A is equal to, on the right hand side, IP 1 plus I to the power of n over 1 plus I to the power of n minus 1. And if you have a look in your tables books, this is in your tables books, guys, it's just slightly rearranged, and you'll see that A is equal to, they bring the P out just in front, and then they say it's the same as P by I 1 plus I to the n, there's an I there, all over 1 plus I to the power of n minus 1. Now, in the question, wherever you see an n, it should be a t, because they've used t instead of n, but it's exactly the same idea. And this here is called your amortization formula. Okay, so it's your amortization formula. And you can use this, you can put numbers straight in, but you can only use it if the first payment is made a month after, or one time period after you've taken out the loan. That's really, really important. That's the only time you can use this formula. If you make a payment on the same day that you take the loan, you cannot use this amortization formula. So it only works if, and only if, the first payment is one time period, which is usually a month after you take out the loan. Now guys, this amortization formula has come up on the exam before. You need to be able to derive it. If you're unsure, then let me know. It's in your book as well on page 226. Now for part 2, it's really, really straightforward. All you do is you just stick in the values. I'll just move the page down and we'll just quickly do that. So if you look at the top of the slide again, what you'll notice is, you go back and just have a quick look before getting back in here. So for part II, just very quickly, what we know is we are taking a loan, okay, of, I think it's 10,000, is it? Yeah, 10,000. My interest rate is equal to 5%, so that's 0.05. And my time period, T is equal to 10. So using the formula, A is equal to P by I over 1 plus I to the power of T all over 1 plus I to the power of T minus 1. Just stick in the values. A is equal to 10,000. Okay, multiplied by 0.05. And you've got 1.05 to the power of 10 all over, doesn't matter where you put it, all over 1 plus I, which is 1.05 to the power of 10, and then what you end up with is minus 1. You put it into your calculator, guys, and get an answer. And in this particular one, A is equal to 1295.0457, and we always write it to 2 decimal places because it's money. So this one is 1295.05. So what we're saying here, just to summarise what this means, is if we take, we'll go with a car loan of 10,000, where the interest rate is 5%, and we pay it back over 10 years with one yearly payment, then the yearly payment will be €1,295.05, and obviously we have to pay that 10 times, which means for the car, instead of paying 10,000, we're paying 12,950. So nearly 13,000. So we're paying almost €3,000 in interest there. Okay. So to sum up, here's your amortization formula. It's in your tables book, as I said. So you've got the amount that you're paying monthly or yearly is equal to your amount borrowed, P, the interest rate is I, and the number of years or number of months that you're paying back is given by T. And this is in the tables book. And again, guys, I can't stress this enough. You can only use this when there's a single loan, i.e. it's just taken out, for example, 50,000, and it's paid off completely with interest by a series of equal regular payments starting one period after the loan is given. One period, that's the important bit. Okay. Now it says it can be adapted to repayments over any regular periods of time, not just yearly. So, for example, monthly. And what we have to do then is we have to change our I to reflect that and our T. So, for example, if we were told that the interest rate was 6% per annum, then we'd have to work out the monthly interest rate if we were paying monthly, and also the number of repayments. If it was 5 years, if it was monthly, it wouldn't be 5 repayments now, it'd be 5 times 12, so there'd be 60 repayments. Okay, what we see here, it says that loans tend to be repaid on a monthly basis, and what we're going to do here is we're going to look at that in the next example. Okay, David and Jean take out a mortgage, okay, which is just a big loan to buy a house. They agree to repay the loan plus the interest by a series of equal monthly payments. So what the mortgage is, starting in 1 month's time and continuing for 20 years. And the effective annual rate of this interest is equal to 6%. So this would be a bog standard question, guys, whether it be a loan or a mortgage. Well, a mortgage is just a big loan. Okay, so it says, first of all, find the monthly interest rate that is equivalent to an effective rate of 6%. Give your answer in decimal form, correct to 8 decimal places. Then use a geometric series to find the monthly repayment, and then use the amortization formula to check this answer. Okay, so let's have a look at the first part. So what we are told is that the effective annual rate is 6%. So what we know is that our monthly rate, I, is going to be equal to 1.06 to the power of 1/12, because we're trying to take the 12th root of that in order to work out what our monthly rate is going to be. Don't forget we need to take away 1 to get the actual rate as well. So our I here is equal to 0.004867551. And lads, we did this in the last section. Okay, so this is where this interest rate is coming. It's the annual rate taken to the power of a 12th, take away 1. Okay, so it's really important that we know how to do this, because we're going to need this quite a lot when we're working out financial maths. Okay, now that we have that, that's the first bit. It says use a geometric series to find the monthly repayment. Okay, so essentially it's just setting up what we did before. Okay, so if you think about it, what's happening here is we draw the timeline. At this particular bit we're getting P, and then we're getting a whole load of amounts again. So we have to pay all these monthly payments. And we're bringing them back, and we're discounting like we did before. Yes, this one needs to come back to the P. This one's coming back 2 time frames. This one's 3, this one's 4, and this one's going to be whatever n happens to be here. We'll work that out in a second. It's 20 years, so it's going to be 20 times 12, which is this one here. This final one comes back 240. Okay, so we do a little bit of a trick here, because it's just a bit of a pain in the hole trying to put things into the formula with all of the fractions. So what we can say, we know this is going to be a over 1 plus I. This is going to be a over 1 plus I squared, and so on and so forth, guys. I think you're getting the idea of this. This is 1 plus I to the cube, and so on and so forth. We get at the end 1 plus I. For this particular one, as I said, there's going to be 20 years of monthly payments, so that's 20 times the 12 months, which is going to be 20 times 12, which is 240. Okay, so it's going to be 240 payments. So there's going to be a lot of payments to pay off this mortgage. Okay, we are all happy that this P is equal to the sum of all of these payments, i.e. this plus this plus this, and it goes all the way to this, which now means that we have a geometric progression. And if you can't remember what the formula was for that, you should have your tables book open anyway. We know that S of n is equal to a 1 minus r to the n all over 1 minus r. Okay, so there's the formula. Now what we do in financial maths is we just use a little bit of a substitution just to help us. And the substitution we're going to use is this. We're going to say, well, let v equal 1 over 1 plus I. Okay, so that means that we can change our stream here. So what we have is P is equal to A by 1 over 1 plus I, which is the same as A by V, plus A, well, that's 1 over I squared, which is V squared, plus A V cubed, plus, and we just carry on. And you see at the end there, we're going to get A V to the power of 240. Now what we can also do is we can actually use our calculator to put this into our calculator and then save it to one of our memory functions. Now if you're not sure how to do that, let me know and I'll make a video about it. But what we can do here is we can put, for example here, we can get our 1 over 1 plus I. So 1 over 1 plus, and our I is this is our monthly interest. So what we do is we put 1 over 1 plus that, and then we send it to our memory function of A or B or whatever you want to send it to. If you're not sure how to do it, guys, somebody let me know and I'll do a quick video again, remind you how to do it. We have done it, but if you're not sure, I'll go through it again. Okay, so from there, what we do is we now know that this here is my A, okay, and in order to, so A is equal to AV, in order to get from here to here, we're multiplying by V, so R is equal to V. My common ratio is equal to V. And now we can just stick it to the formula. So I'll go back to black. We've got S of n now is equal to A1 minus R to the n all over, and we've got 1 minus R. And then we just stick everything in. So S of n is equal to A, which is A by V, 1 minus R, which is V, and to the power of n, which is, we've said it's 240 payments for this one. And that's all over 1 minus R again, which is V. Now, you should have V in your calculator, in one of your functions that holds a memory, one of your memory functions. So put it through, put everything in, and what you should get from here is that Sn is equal to something in terms of A. And if you do that, you should get an answer, guys, of 141.384.309A. And that there is the sum of all of these payments here. Okay, so it's the sum of all these payments here. That's what we have there. Now we know that they took a loan of 200,000 to pay the house, so we've got 200,000 is equal to 141.384.309A. So in order to get A on its own, we need to divide this into this. And if we do that, guys, to 2 decimal places, we get an answer equal to 1414.58. Okay, and that there is the amount that they have to pay on a monthly basis to service a €200,000 mortgage. That means every month that they have to pay €1,414.58 for the next 20 years in order to service this loan. Okay, hopefully that makes sense. Right, let's see if we can get this to work with the formula. Okay, because we can just use the amortization formula, so we're just going to check that now. So here we go, just move that up. So we've now got III, and the amortization formula, if you remember, is A is equal to P, okay, and it's I1 plus I to the power of T, okay, to the power of T, all over 1 plus I to the power of T minus 1. Stick the numbers in, guys. A is equal, your P is 200,000. Your I in this particular one is equal to 0.004867551. Remember, it's the monthly one. Okay, that's the one that we're doing, so it's the monthly one. Okay, and that there is to the power of the number of periods that we're doing, and remember it's 240 months all over 1 plus, and the I again is 0.004867551, okay, to the power of 240 minus 1. Guys, stick that into your calculator and you will get 1414.58, which is the same as if we were using a geometric progression. Now, if you are given a basic question and it asks you to work out the mortgage repayments, i.e. A, it doesn't matter which one you use. It's obviously easier if you realise that we can use the amortisation formula. It's obviously easier to use this one than it is to use this particular geometric progression, but both are correct. The main thing is, guys, is you've got to remember that you have to change an annual rate into a monthly rate. That's the first thing you have to do. And then you have to remember that means that your time or the number of payments has changed. So, for example, if it's 20 years, then there's now 240 payments on a monthly basis. That's important as well. Okay, so just before you attack a question on an amortization question like this or a loan question, make sure that you work out what your interest rate is that you're going to be using and what your time frame is. The P is normally fairly obvious. This slide just quickly shows how an amortization schedule works, and essentially what happens is at the beginning of a loan, what you're doing is you're paying off a lot more of the interest portion of the loan than you are the actual principal. So a lot more interest is paid at the beginning, a lot less, and when you see what's happening is you're paying a bit more of the principal off, then that means you're paying less interest, and eventually it gets to a tipping point where you get to a point where you're then starting to pay off more of the loan than you are of the interest. You can see that's towards the end of the actual loan. So a lot of an amortization loan is interest at the beginning and principal at the end. Okay, the last thing that we have to look at here. Okay, it says Serena borrows 50,000 from a bank to fund new machines for a business. She agrees to repay the loan plus interest by a series of level annual repayments, so the same amount, starting 1 year later and continuing for 6 years. The agreed annual interest rate for the loan is 7.5%. Right, this is perfect. So she agrees to repay the loan plus interest level or series of annual repayments, which are the same, starting 1 year later. This here is music to my ears. That means now that I can start using the amortization formula. So all I'm going to do is just run that through to get the first one. So find the amount of each annual repayment, straight into the formula. Remember, it's A is equal to P, and we've got I, we've got 1 plus I to the power of T, and it's 1 plus I to the power of T minus 1. Our A here is what we're trying to find out. So A is equal to our P is, that's what she's borrowing, 50,000, that's the principal. We have 1 plus I, so that's 1 plus 0.075, and do that in our heads, 1.075 to the power of T, which in this case is 6 years, all over 1.05 to the power of 6 minus 1. Stick it into your calculator, boys, get an answer, and you should get 10,652.24. So that's just sticking it straight into your calculator. Okay, then it says construct a schedule showing the interest and principal portions of each of Serena's annual repayments. And at the end of 4 years, Serena finds herself in a position to clear the loan. How much will she have to pay the bank at this stage? Right, okay, part 2, I'm going to go to a different slide, and I'm just going to show you what's going on with that, and I'm going to talk you through it, because it'll probably be easier than me trying to construct it. So, for part 2, what we have here is what's called a schedule of payments, or an amortization schedule. Okay, so this is what we do. We just follow these instructions in order to work this out. Okay, so I'm going to talk you through maybe the first couple of lines, and then hopefully you can see what's going on. Okay, so the first thing we do is we enter the amount borrowed as the balance of the first line. So payment number 0, you can see we set it up fixed payment interest principal balance. So 50,000. So we've not paid anything off. Now, we enter the fixed payment. Now we calculated that in the last slide to be 10,652.24. Okay, and what we do is we put that in. Now what we do is we fill in it row by row. In each row, calculate the interest by multiplying the balance from the previous row. So what we do here, okay, so you can see it. In order to find out what the interest is due on this, what we do is we take this part of the interest here. What we do is we take the previous balance, which is this, so 50,000, times the interest rate, which is 0.075, which is 7.5%. If we work out 7.5% of this, you'll find it's 3,750 euros. So we put that into the interest. To find out how much principal then we've paid off for this year, what we do is we take the fixed payment, which is 10,652.24, and we take it away. Okay, so we take it away in order to get that as my principal. Okay, so that means that in the first year, I've paid off 3,750 in interest and 6,902.24 of the principal. Now, in order to find out how much I now owe for the next one, you can see here that this, taken away from this, will give me how much I actually owe, or the principal, for the end of the first year. I'm then just going to repeat the process, guys. So to find out how much interest I'm going to work out for the second year, I get this balance here and I multiply it again by 7.5%. And you'll notice it's going to be less than this one because it's a smaller balance. So 7.5% of this value is now this value. I'm then going to do exactly the same thing. I'm going to get my fixed payment. I'm going to take off the interest like I did here. And that now means I'm going to pay a little bit more of the principal off because I'm paying less interest. In order to find out my balance at the end of the year, again, what I do is I take this number away from this number and I'm left with this value. And I complete, and I can keep doing this row by row by row until I get to the end and I get a value of 0.00. Now, guys, sometimes you might get 0.01 or 0.02. You might be a couple of cents out. That doesn't really matter, okay? So that might just happen to be 0.02 on account of rounding errors. And that doesn't really matter. The last part of the question says, if I remember rightly from the other slide, it says at the end of 4 years, Serena finds herself in a position to clear the loan. So at the end of 4 years, so here it is, she can pay off the loan. She doesn't have to pay any more interest. What would she have to pay? Well, you can see here it says 19,126.80. So if I had the money at the end of the fourth year, the only thing I'd have to pay is 19,126.80, which means I'd save this interest payment and this interest payment, which is the guts of £2,000. So by paying it off early, I'd save nearly £2,000. Right, guys, there's a lot in this slide. I'm going to give you a couple of days to practice this. Are there any questions? Then just let me know. Okay, good luck.